Good evening, class. All right, we're continuing along with mass storage systems. Today we're looking at disk management, swap space management, RAID, and stable storage. Here are the chapter objectives one last time. The unit of storage on a disk is a sector, which is typically 512 bytes. And then error detection or correction codes are kept to ensure the integrity of the data. And then a sector can also contain header information such as the sector number so that the sector can be identified within its cylinder. So low-level formatting is the process of establishing the sectors on a disk, and with old disks, low-level formats had to be applied from time to time as the read-write heads drifted with respect to the disk itself. Then the next stage in preparing a disk is partitioning it, which partitions it into groups of cylinders, each of which can be treated as a logical disk. So in Windows, a different drive letter, or in Linux, just a different disk. Then once the disk has been partitioned into logical disks, file systems can be created on those logical disks. In a Linux system, one would typically create a root file system, a boot file system, and finally a third partition for swap. And as mentioned, to decrease the bookkeeping within the file system, blocks, that is sectors, are usually grouped together into a number of clusters, so the file system doesn't necessarily allocate 512 byte blocks. They could typically allocate larger blocks with of course, with a certain amount of internal fragmentation coming along as baggage. So swap is often done as its own partition, simply to cut out the file system and make the swap I/O more efficient. But as mentioned here, other application software will sometimes access raw partitions for their own uses. As we'll see in the next slide, the first sector on a disk is the boot block, which stores the bootstrap program and the partition table. Also, MBR stands for Master Boot Record. That's the boot block, which contains boot code, and in the case of Linux, that would be grub, and the partition table, which is a table which describes the partitions on the disk. One of the decisions that has to be made when designing swap space subsystem is when to back up processes, pages to the swap device. Here we can see 4.3 BSD allocates the swap space and stores the text segment and the data segment when the process starts. In some sense, it might be most efficient to not allocate swap space until it's needed. Another design decision would be what to do with the text segment, because program code is, of course, in the file system, so it doesn't really need to be stored out to swap. But if swap is its own partition, loading it reloading it from swap may be faster than reloading it from the file system. If a system runs out of swap, well, perhaps there's a process to take care of that situation and start terminating processes. If I recall correctly, some older versions of BSD Unix would suffer a kernel panic if that happened. And I can remember once upon a time there were various rules of thumb as to how much swap space to set aside for a given amount of memory. Typically these days when I'm setting up a system, I'll ensure that I have at least as much swap as I have main memory. Sometimes I'll go twice as high. Linux systems allow you to have multiple swap partitions. If I set up a system with multiple disks and I have enough space, I'll typically set up a swap partition on each disk to provide some parallelism and speed up swap IO. So here we see a Linux swap area partitioned into page slots, and the meaning of the swap map, an entry of 0 means that the page slot is not in use. A non-zero swap map entry indicates the number of processes that are using that page slot. So here, for instance, 3 processes are using this particular page slot, which implies that they're sharing memory. RAID is a family of techniques for combining a number of physical disks into a single logical disk in order to increase performance or increase reliability, or perhaps even both. RAID level 0 performs striping. So let's say that we have 2 physical disks. Even logical blocks are stored on one disk. Odd logical blocks are stored on the other disk. So what this allows us to do, if the file system requests 2 adjacent blocks, rather than performing 2 sequential IOs, 2 parallel IOs occur. So this doubles the bandwidth of the disk subsystem at the expense of, if one of the physical disks fails, then the entire RAID system has failed. So with striping, your fail rate will double. With mirroring, you have, let's say again, 2 disks. They're exact copies of each other. So in this case, read operations can, reads to 2 adjacent blocks can be done in parallel, one from one disk, one from the other disk. Writes, a single write to the logical disk entails 2 physical writes in order to maintain the mirror. The only other RAID level I'll talk about that is commonly seen is RAID level 5 that introduces, as you can read, a parity block. All right, so here's a figure. So here we have RAID 0 striping. So imagine logical block 0, 1, 2, 3, 4, 5, 6, 7. Here we have mirroring. So these 4 disks are mirrored by these disks. And then finally, we have RAID 5, which for every 5 blocks of data only 4 are actual data blocks. The 5th is a parity that allows us to detect and recover from errors. I'm going to skip this. I'll also skip this. I'm going to skip this. I'll skip this. All right, I'll spend a minute here. Traditionally, a number of disks are combined into a volume, and then a file system is built on top of that. The problem here is at the time that you're building the system, you have to know how large each file system needs to be. Otherwise, if you guess wrong, you're stuck with backing up the data perhaps and rebuilding the volumes, recreating the file systems, and then restoring the data unless unless of course you have a tool that allows you to do this automatically, which or manually. With your virtual machines, I increased the size of the virtual disk and then used the genome partition editor to allocate more space to the file systems without having to do the backup and restore step. A more elegant solution is to use pooled storage. In Linux, there's LVM, the Logical Volume Manager, that allows you to simply, in essence, pull your disks into a storage and then dynamically allocate space as needed among your file systems. So a write-ahead log is a technique used in file system design to maintain file system integrity when, say, power is lost to a system. And when that happens, it's possible that not all disk writes have completed. So a record of pending writes is kept in the write-ahead log. As mentioned here, that requires stable, non-volatile storage, and which means that the data is replicated in some manner. So in terms of a disk write, we have these 3 outcomes. Either the write's successful. At the other end of the spectrum, we have a total failure, in which case nothing has changed. And in the case of a partial failure, that will be detected and the original state of the disk restored. Right, so that recovery procedure is outlined here. It's not uncommon for disk storage subsystems to use non-volatile RAM as a cache within the storage subsystem and also to help implement stable storage. All right, so that finishes chapter 10.